Hello and welcome to this presentation on Subarrays with sum k. In this session, we will explore how to efficiently find contiguous subarrays in an array whose sum equals a given value k. We will be using the approach of prefix sum and hash map to solve this problem. Let's begin with the problem statement. Given an array of integers and an integer k, the task is to find the total number of contiguous subarrays whose sum equals k. For example, consider the array containing the elements 1, 2, 3, 4, 1 and the target sum k equals to 5. The output will be 2 because the subarrays 2, 3 and 1, 4 both sum up to 5. Now let's dive into the approach we will use to solve this problem. First, we calculate the prefix sum of the array, which is the running total of the elements from the start of the array up to the current index. We also use a hash map to store the frequency of the prefix sums we encounter. This helps us quickly find if there exists a subarray with the desired sum. For each element, we calculate the current prefix sum and check if the difference between the current sum and k exists in the map. If it does, it means we have found a valid subarray. Let's go over some key concepts. Prefix sum. This is simply the sum of elements from the start of the array up to a given index. Hash map. It allows us to efficiently store the frequency of prefix sums we have seen so far. Checking subarrays. If the difference between the current sum and k exists in the hash map, we can be sure that a valid subarray exists that sums to k. Here's a breakdown of the algorithm steps. We initialize the current sum to 0 and set the frequency of the sum 0 to 1 in our hash map. We iterate through the array, update the current sum by adding the current element. We then check if the difference between current sum minus k exists in the map. If it does, we add the frequency of this difference to our result count. Finally, we update the map with the current prefix sum. At the end, we return the total count of valid subarrays. Here's the first part of the C++ implementation. We define a function subarrays with sum k where we initialize our variables. A hashmap prefix sum freq to store the frequencies of prefix sums. Current sum to track the running sum and count to count the valid subarrays. We initialize the frequency of sum 0 to 1 in the map to handle subarrays that start at index 0. Now let's move on to the main logic inside the function. We look through each element of the array. For each element, we add its value to current sum. Then we check if the difference between current sum minus k exists in the hash map. If it does, we add the frequency of that sum to the count. Finally, we increment the frequency of current sum in the map so we can use it for frequent iterations. Here's the main function that runs the code. We initialize the array and the target sum k. We then call the function subarrays with sum k and print the result, which gives us the number of subarrays that sum up to k. Let's walk through an example to see how the algorithm works. Consider the array containing the element 1, 2, 3, 4, 1 and the sum k equals to 5. The prefix sums we calculate as we move through the array are 1, 3, 6, 10, 11. We also update the hash map as we go. When we check the sum 5, we find that current sum minus k equals to 0 exists in the map. meaning we have found a valid subarray 2, 3. In total, there are two subarrays 2, 3 and 1, 4, both of which sum to 5. Now let's look at the time and space complexity of this approach. The time complexity is big O of n, where n is the number of elements in the array. This is because we are iterating through the array once, and each map operation, insertion and lookup takes constant time on average. The space complexity is big O of n, which amounts for the space used by the hash map to store the frequencies of prefix sums. In conclusion, this approach using prefix sum and a hash map allows us to efficiently find subarrays with a given sum in linear time. This method is much faster than a brute force approach and is optimal for handling large arrays. Thank you for your attention, and I hope this solution helps you understand how to approach similar problems.